All right, welcome back. So next up, we will have Eddie, who will tell us about IBM's vision for building a fault-tolerant machine using the gross code. Please take it away.
Hello, and thank you all for coming. This was a collaboration with many folks at IBM, and I'm very happy to present it to you all here. Thank you for coming. So to kind of kick things off, I'm going to maybe contrast our approach a little bit with a surface code architecture of building a quantum computer. And as we may know, if you build a surface code qubit, we know that if you want to have one logical qubit, the surface code requires 2 times d plus 1 squared physical qubits. Maybe a year ago, or was it 2 years ago, the IBM team introduced these bivariate bicycle codes. And in particular, we're interested in the gross and 2 gross codes, which have a distance of 12 and 18, respectively. So the gross code has a distance 12, and it decodes 12 logical qubits at the cost of 288 physical qubits. And the 2 gross code has a distance of 18. And it also encodes 12 logical qubits, but it requires double the physical qubits, 576. So if we compare that to the surface code, which encodes 1 qubit, that requires also 288 physical qubits. I guess I did the math a few days ago. And at distance 11 and 578 at distance 17. So we get roughly an order of magnitude more logical qubits for our physical qubits. This picture is reiterating that even if we encode our logical qubits into this gross code, we can expect maybe roughly on the same order logical error rates while only spending 10 times fewer physical qubits. So this really motivated IBM to pivot to these bivariate bicycle codes because building physical qubits is expensive. So if we can save a factor 10, then that would be great. Of course, that it's not so simple. So the gross code can be visually represented by its tenor graph, which can be embedded in a torus. Here we have all the syndrome checks represented by these z's and x's, and they are nearest neighbor except for 2 long-range connections, which are depicted here in purple for a few of them. And it's exactly these long-range connections that have made these LDPC codes hard to implement in these kind of superconducting architectures. And to kind of demonstrate to you, or give you at least an idea that IBM is making progress in this front, I've included some hardware demo slides that show some of the advances that we've been making, and hopefully give you some confidence that this is a feasible approach for the future. So one thing you may notice is that the degree of the nodes here is no longer of a degree 4, or as in the surface code architecture, but really require degree 6 connectivity. So the first demo is to show that indeed we can build a small device with a couple of qubits that has a degree 6 connectivity and also has a good gate fidelity, so we don't lose much gate fidelity. The second is that we can actually implement these long-range interactions. So in purple here, I wrote the gate fidelities, although this one is missing. I copied these slides from somewhere else, so sorry for the quality as well. I can see that on the screen it's not amazing. But yeah, so the gate fidelity is still preserved, even over these amazingly long distances. And third, the connectivity that is required has these non-planar connections. So we needed to add another layer of interconnect, because we know that this gross code can be implemented using so a biplanar interconnect, 2 layers of planar connections. And here on the left, you can see that on the chip, we add an additional layer of interconnect on top. That's that second layer. And the experiment showed that versus a planar interaction, the biplanar interaction, so the one that uses this interconnect, also has a similar gate fidelity. So kind of getting back to the architecture design, sort of the conventional approach for many years was to assume we have this very large monolithic hardware that has a bunch of short-range connections. So maybe imagine some ginormous chip, if you're doing superconducting qubits, that implements a whole bunch of these surface code qubits on there, right? So you divide up this giant sea of gates and you build a whole bunch of surface codes. But now with the innovations in these long-range gates, we can not only build a gross code on a chip, which is fairly compact. As I said, you can fit about 10 times more logical qubits in the same amount of space. If we additionally add long-range connections between chips, so those are so-called L couplers, we can combine them together to build a larger architecture. So we have gross codes, each of which encode 12 qubits, and then we connect them together using these L couplers into a large, scalable, sort of modular architecture. Yes?
Just to recap for myself. So there's like the qubits, and then you have connection on the bottom and on the top. The way I should think about it?
You mean on this slide? Or?
I guess, like, how does it physically work?
Oh, I see. Well, so I'm not an experimentalist, so I'm the wrong person to ask. But so we have this chip here on the device, and we have connections here in black. That was the first plane, and on top we have another plane of these couplers between.
Like, what the limitations of the like a double layer something lattice, or?
Yeah. So these are two planar graphs that are stacked on top of each other, and they have some of these like vertical connections in this image.
So can you say what graph these long-range edges look like? So is every, so presumably every vertex has degree 2 for what you were saying.
So
long-range edges.
So the vertices, we actually require degree 6 connectivity.
Yeah, I know, but I'm assuming 4 is for the local connectivity and 2 is for long-range.
Oh, I see. Actually, when we implement these codes, it is not going to be some kind of regular layout. They have some advanced tools that scramble up your graph so that they can bake the chip efficiently and minimize the connection length in some way. Yeah, I can't really say that you will have a degree 4 on this plane and a degree 2 on the other plane, because things get scrambled up when experimentalists look at it.
But the long-range connections are a planar graph.
Well, so they could use these vertical connections to go up and back down.
Right, but I'm asking whether when you go up and go down, your extra layer is still planar, right?
Yes. But if you write this as a graph, it might seem like it's non-planar because you went up and back down, so you're going over some other edge.
I meant just the top layer. If you forget about the bottom layer, then it's still a planar graph.
Yeah. Okay, thanks. Any further questions before I continue? Yeah.
Can you go on? Can you like stack more layers?
I don't know. Yes?
In the modular hardware, you have this chip for 12 logical qubits. And then you have many of those, so it's easy to fabricate and
Yeah.
have higher yield.
Yeah. Yeah, so that's a major reason why we decided to have these smaller chips, because fabricating one ginormous chip perfectly is nigh impossible, because you have some probability of failure for every one of these gates, so you have some exponential likelihood that one gate will be faulty. So that's why we have this modular design now, where each chip, with some probability it might fail, like maybe 50-50. I'm just saying random numbers, but that means you can still keep half your chips and build the architecture post-selecting all that. It was successful.
So,
Yeah.
like, what do these interconnects look like?
These interconnects, yes, I will. Let me see. Maybe I have a slide very soon. Yeah. Okay. So to kind of convince you that building such a bicycle architecture, as we call it, has good capabilities, we have this plot that I will reveal slowly. So we're going to estimate the logical capability of this bicycle architecture and compare it to a conventional surface code architecture. And in this plot, we plot the logical qubits in the architecture versus the number of T-gates that can be performed. And roughly, such circuits are classically simulable if you have more than 75 logical qubits and more than 75 T-gates. These are very rough estimates, don't hold me too much to them. And of course, the algorithms improve, and depending on what you select, you can simulate more or less. The scientific toy models live up here. So for example, the transverse field Ising model requires, of a 10 by 10 to the transverse field Ising model requires 10 logical qubits and 10 to the 7-ish T-gates. And if we take the convex hull of such problems, then we get a region like this. Cryptography, we have a couple of problem instances here, extremal problem instances, and so the convex hull looks like this. It requires more logical qubits, but also more T-gates. And quantum chemistry, we estimated it to be somewhere up here, where maybe you require less qubits for some instances, but more T-gates, and there's some space-time trade-off here as well. So if you can do less T-gates, but you have more qubits, you might still be able to do interesting problems in the chemistry. Yeah?
Just to understand this figure, that's roughly you're saying the TFAM is inside this unexplored classically regime?
Yeah. So this is a lot.
Simulable, can you explain this?
Yeah, so the 2D transverse field Ising model.
The 2D, okay, great.
Yes, it's not 1D. Yeah. Okay. So before I can, yeah. Good. So the smallest instance we looked at, and maybe the simplest one, we assume we have 5,000 physical qubits. They're given to us, and each of these physical qubits has a physical error rate of 10 to the minus 3. What kind of architecture can we build out of that? Well, if we take 5,000 physical qubits, we can build a bicycle architecture with about 100 logical qubits that can perform about 10 T-gates. This is, it might sound not that impressive, but it's not a T-gate in the conventional sense, but it's Clifford gates and then interspersed with 10 T-gates. So any Clifford circuit interspersed with T-gates. So these are global type operations. And if we take a comparable surface code architecture and give them the same physical resources, so 5,000 physical qubits and 10 to the minus 3 noise rate, we can find a comparable surface code architecture, I think it's distance 7, that has fewer logical qubits, but can do about the same number of T-gates. So that's how we compare the two. So let's say we reduce the physical noise rate, then we can build a much better architecture. So with the gross code, we have, again, about 100 logical qubits, and the surface code, to achieve that same capability as in the number of T-gates, we need to sacrifice more of our logical qubits. So this is actually, I think, a distance 9 surface code. So you need to up the distance to get the same capability. Now, if we have, instead of reducing the noise rate, we increase our number of physical qubits by a factor 10, we are actually capable of, you could build a 2 gross code architecture here in this blue ellipse with still a fairly, a worse physical noise rate. But this 2 gross code architecture has much more logical qubits, thanking to the 5,000 physical qubits you give it. And the advantage it has over the comparable surface code architecture is much more pronounced. So you get much more logical qubits while having the same T count. And I must say that, for the surface code architecture, obviously you could choose to have more qubits but worse noise rate by dropping the code distance. So there's some parameter regime of surface codes that is not depicted here. Sorry, question?
These black squares, they represent surface codes on superconductor.
So these surface code architectures, they're hypothetical. It's a very simple theoretical model of a surface code architecture with these parameters. So we have 5,000 physical qubits and 10 to the minus 3 physical noise rate.
So it's something like the game of surface codes where everything is in a 2D.
Yeah,
situation.
something like that. Yeah.
Okay, thank you.
Yeah.
So these numbers, I assume, represent these speakers.
No, we use the same magic state factories to compare the two architectures. The only difference here is the type of code that we're using, and yeah. I mean, a lot of things go into getting to this data point, including generating random circuits. Getting noise estimates, things like that. But for the surface code architecture, it's a simple equation that you could solve, on pen and paper very easily. Okay, yeah.
Sir, so how do you calculate this logical T count? Is this, why can't you just, I don't know, distill more? What limits this logical T count? Is this fundamental?
So this logical T count is a function of the physical error rate and the number of qubits that you need to perform gates on. So obviously, if I tell you, oh, you need to do just T gates, then you can do more of them. But if I say you need to do a T gate and inject it into a computer that is 10,000 logical qubits wide, then all those additional gates that are required for that require more, will result in more noise in your system. So the capability here is when do you hit 1/3, say, failure probability, right? So, let's say your gate has 10 to the minus 5 logical error rates. That means you can do roughly 10 to the 5 of them before you hit that 1/3 barrier, and you will fail with high probability. So the surface code hits that point here if we require that the logical T count is similar to this data point. So these data points we calculate it, and then we find a comparable surface code architecture and see that the capability in the number of qubits is improved. So if we reduce the physical noise rate, then the 2 gross code actually improves by a very large amount, so 10 orders of magnitude, and we might estimate it is capable of executing certain quantum chemistry applications at 5,000 physical qubits. And again, if we also improve the number of physical qubits, so we're talking long term, then we will also be able to do some crypto applications. Yeah, question.
So do you think it's realistic to get to 10 to the minus 4 physical noise rates?
Yeah.
Olaf was kind of mentioning this, like, okay, we can do this and this and this, and this kind of decreases our error budget somehow. Like, do you have like similar?
Well, I'm kind of the wrong person to answer with this physical noise rate is realistic, but we kind of picked some representative data points, and I'm not saying we're going to build a device with exactly 50,000, but they're just kind of to show you the range of parameters that are required and for our current understanding of these architectures. And these data points are expected to shift around massively over the coming years. So we might find new chemistry applications that require much less qubits or things like that. We might have algorithmic, improvements in compiling for these architectures, which will shift the capabilities up at lower noise rates. I have another plot that goes into detail for this transverse field Ising model that maybe will be a bit more that you might be interested in. So let's see. Yeah. Any further questions? Because I have all the information right now. Okay.
Sorry, just going back to Umesh's question. If you were to take like cultivation or that type of technique into account, do you know if this picture would change?
Yeah, so we do use cultivation for the data points that have 10 to the minus 3 noise rate. For 10 to the minus 4, we have some distillation factories. Yeah. And, our paper really, we have a section that analyzes which factory we would use in which instance. Yeah. Okay. All right, so what does a bicycle architecture actually look like? So we have our gross codes here in the bottom, but these gross codes, they are only a memory. We can only store quantum information, and if we want to do a computation, we attach this Ancilla system to the gross code, which we call logical processing unit. And by connecting these logical processing units through a bridge system, this B, together with L couplers, which are the wires I alluded to earlier, and I will show a picture, I think, in the next slide, we can perform joint measurements between two of such gross codes. And this logical processing unit can do in-module measurements, so it can perform measurements of certain qubits inside this gross code. And together with a magic state factory, we're going to construct a universal computer. So we connect many of these code modules, as we call them, together with L couplers and some magic state factory. And together, this forms a bicycle architecture where we can, plug in here either a gross code or two gross code. And this will allow us to do universal computation, as we showed in the paper. I don't know if there are any questions. Okay. So these L couplers, as Dominic asked, okay. There was a demonstration where we have L couplers connecting some qubits in a fridge, and these wires are about 1 meter long. And the demonstration showed that we could do some entangling operation with a 96.5% fidelity at a distance of about 1 meter. So the idea is that we connect many of these chips together with L couplers so that we're able to generate sufficient entanglement to do our operations fault-tolerantly. Okay, so let's say, let's compute sort of how much qubits our system costs. So if we have our code C and our LPU logical processing unit U, and we have our interconnect A, there are various ways we can connect our system together. For example, in A, we just show a linear connectivity, but many things are possible. So for example, this is actually a sort of a triangular connectivity together with a factory. Then the physical qubit counts of our system, I have tabulated here, copying, and these results are also in the paper. And you can see that the physical qubit counts are respectable, not massive, except for this factory at 10 to the minus 4. But this was sort of a rough estimate going off of the distillation literature. And we expect that could be improved, with further research. Yeah.
So for the fidelity of your L coupler, am I right in thinking that you eventually want that to be 10 to the minus, your error to be 10 to the minus 3 there too?
Yeah. So that if it's 10 to the minus 3 at the logical level, then it would fit the simulations I showed you earlier on the logical capability plot.
Sorry, and so the figure that you gave in the last slide.
Tape this one, right?
Yeah.
Yeah.
So you have to improve the fidelity to 99.9, or is this? I'm a little unclear whether this was sufficient for what you said.
Yeah. So this is not sufficient because we require 10 to the minus 3 logical error rate. Well, actually, yeah. So this fidelity would allow us to create bell pairs, and then through some processing, we might be able to distill a better bell pair, for example. Or maybe at a logical level, we can achieve a better fidelity by performing many of these gates. So actually, I'm not sure if it's sufficient or not. We just demonstrate that it's possible to do a gate at a long distance.
It's not so clear, right? Because like if you just do like a interconnected circuit codes, right, and you have like, let's say, coming some region where you have like some coupling where like the error rate is like non-homogeneous, like where the error is like increased.
Yeah.
Actually, you can like if the threshold in the bulk is at 1%, you can actually kind of you can deal with like 10% on the boundary.
Yeah.
It's kind of like population theory argument that it's like essentially like a population problem in like one dimension lower.
I see.
Which increases the threshold. So I don't think it's like super obvious that you would need like such a high.
Yes. Yeah. When I thought about it, I realized that you might be able to deal with worse fidelities at these long-range interconnects, and that's something. We expect that these connections will be worse than the on-chip coupling, so we have to deal with it in some way. Yeah.
Sort of in that same vein, like, so as Nico was saying, there's these like seam effects where you can have a high threshold with like 1D cut, or high like error rates and accept it. But for your, I think they're called M couplers, the like long-range in-chip couplers, those are bulk distributed. So if those are also slightly noisier, how does that impact your threshold? Do you have a sense for like, if you have like a factor of 2 or something, is that going to dramatically impact performance?
Yeah, I guess I don't really have a sense of what that would be like because we haven't run those simulations. We kind of assume a fairly uniform noise model in the architecture, so I don't know for sure what the impact would be. Yeah.
How is the code distance preserved while we are transferring information from one code block to another code block through the outcome?
Yeah, so you can imagine that we have that information that we want to transfer, and we encode it in some redundant way, right? So for example, if we want to teleport a qubit from one code module to another code module, what we're going to do is some kind of joint measurement between the system, and this joint measurement needs to have a low failure probability to be successful because it's one of those basic building blocks that we need for building a large-scale architecture.
Okay, can I view the L coupler itself as a error correction code where the distance is at least as good as those of the blocks?
So the L coupler really is a hardware primitive. It's a wire, connecting a fridge. But on top of that, we will build a more complicated and robust system that interacts through these L couplers and maintains the code distance. Yeah.
So, one of the features of Silicon platform that started with the fast gates. So what happens with these L couplers? Are they fast as gate times?
Yeah, I also don't know. Thank you for the question.
How far can we transfer one qubit to another qubit, and what is the error efficiency?
Yeah, so these cables are 1 meter long.
1 meter long.
So for a modular system, yeah, hopefully that's sufficient.
Okay, thank you.
Okay, I will continue on. Okay, so using the logical processing unit, we can define a primitive set of operations that act at the logical level, which we call the bicycle instructions. So the bicycle instructions, there are only a few. One is an in-module measurement, so that's this measure qubit 1 in Z and qubit 6 in trivially. We divide up our code modules into registers of size 1, 5, 1 and 5. So qubits 1 and 7 are special in the sense that we can measure them directly. Additionally, there's this automorphism, unitary, which acts symmetrically on the first 6 qubits as well as on the second 6 qubits. What it does is sort of a CNOT circuit on the code module. The third kind of operation is an intermodule measurement, which are these blocks highlighted in red, and they use the connectivity here on the left that is also highlighted in red. These measurements, they use those L couplers that I talked about earlier to measure jointly between 2 code modules. And yet again, there's some bases that we can measure in. So for example, we can measure Zi, Zx on qubits 1, 6, and 1 and 6 on another code module. And finally, if a code module is adjacent to a factory, we can perform a magic state injection in some bases, so Z, Y, or X on qubits 1 or 7. Now that we define these instructions, we're interested in what are their logical error rates. So first, we need to define what decoder we're using, and because our systems are quite fast, we need to have a real-time decoding strategy that has a very, its duration is very short between iterations. So we introduced this relay BP decoder, which is suitable for a real-time implementation on, say, an FPGA or in hardware. And this relay BP decoder improves on previous BP decoders. I think it's called EWA init, maybe, by Chen et al. We call that the MEMBP decoder. And the improvements, are as follows. So the BP decoder has certain beliefs that might oscillate and will never converge. So what MEMDP does is include some memory terms, but this could converge to an uncertain belief. So in relay BP, the memory terms are disordered, so that kind of kicks you out of symmetric trapping sets. And moreover, what also happens is that we do multiple runs of this decoding where we change the configuration of the memory terms. So with one configuration, we might not find the solution, but the next might find some solution. But then we pass it along to the next iteration, which could find a better solution or no solution at all. And this decoder is very fast in the sense that if we allow ourselves only 600 iterations, which is roughly the real-time budget that we have for decoding, we see that relay BP achieves a much lower logical error rate than the MEM-BP decoder and the BP decoder. It's maybe roughly an order of magnitude. And it's also approaching the relay BP decoder that had 10 to the 8 rounds of decoding, which obviously is going to be too slow if we needed to do this in real time. Any questions? Okay, so now that we have our decoder, we can try to see how noisy our instructions are. But we noticed that if we want to do Monte Carlo sampling, we can only realistically sample high error rate regimes. So how do we figure out what happens at 10 to the -3 or even 10 to the -4? It's so unlikely that you encounter a logical error that it becomes unfeasible to simulate using Monte Carlo simulations. So we developed a new technique for extrapolation, which starts with sampling weights of faults of exactly weight W. So let's say we sample sets of circuit faults that have exactly W faults, and we estimate what the failure rate is for those sets. So let's say, we have 30 faults, and what probability does the decoder fail? It gives us a logical error. Then we fit those results to an ansatz, and that gives us this curve, in blue, red, or green. And this curve, when we translate it back to the logical error rate, does agree with the Monte Carlo data at the higher physical error rates that we obtain, or is a bit more conservative than that data. I do need to note that we have a few more data points up here for high fault weights that we did not use for fitting this curve, but that if we do include them, then the resulting curve is actually better. So it gives us lower logical error rates. Yeah, questions?
So what do you mean by sampling a circuit fault?
Yeah, so good question. So so let's say you have your circuit, and we fix W. So then you pick W sites to inject a fault into the circuit, and then you see if your decoder fails or not. Okay. And so in that sense, you can fix W and sample a bunch of configurations and see what fraction of your runs fails, right? For fixed W number of faults. Yeah, so we will have more justification in an upcoming paper by Beverland et al., Michael Beverland. So if we just look on this plot and we look at 10 to the minus 4 or 10 to the minus 3, we get the numbers in this table, which is prominently displayed at the beginning of the paper. And on the left, we list the bicycle instructions, which I introduced a few slides ago, and those are the basic building blocks that the bicycle architecture is capable of performing. So we see that idling, so just doing syndrome cycles, has a certain logical error rate of 10 to the minus 8.8 roughly, whereas the 2 gross has a 10 to the minus 20, say, idling error rate. You can confirm that for the gross code here because, let me see. Okay, yeah, so here for 10 to the minus 3, we have about 10 to the minus 8, 8.8 apparently. And for 10 to the minus 4, we have 10 to the minus 15. So that's where these numbers come from. And when we actually want to perform computation, we need to do these shift automorphisms, measurements, or even intermodule measurements. And you can notice that the error rates for these operations get much worse, right? Especially if we consider intermodule measurements, because these operations require much larger systems to be involved, many more qubits, much more moving parts. So we definitely want to improve the error rates for these very expensive operations, because we think that improving those numbers will push the capabilities of these devices significantly higher. And finally, I will note that the 2 gross code that system is so large for doing in-module and inter-module measurements that we did not have simulation results for those data points. So we give rough estimates without further justification. And the further results that we present are based on the numbers in this table. So if there are any questions, then. Okay. So now let's say, let me check how much time we have. Yeah, until 15. Okay. So let's say you want to compile for the bicycle architecture. I might go over this a little bit quicker so I can go a bit slower in the conclusion. Let's say you're given some Clifford plus T or some small angle rotation circuit. Then using known techniques, you can compile this to a circuit that consists of rotations of that are generated by Pauli. So e to the I p phi rotations. So it's e to the I phi p, maybe more accurately because the angle is a phi, and measurements of some Pauli string. And then I will explain how you can compile such operations to the bicycle architecture. So first off, we need to kind of split up these operations and assign them to various code modules. So let me first explain the language we use. So first off, we use round boxes to denote unitary gates, and in blue we have Clifford gates, Clifford unitaries. And with square boxes we denote measurements. So for measurement outcomes A, which are either 0 or 1. And very frequently we actually don't care about the measurement outcome because we measure in a state that is either stabilized or has some anti-commuting stabilizer. So when we have a state like that, we can actually ignore the measurement result. So if we don't write a measurement result, what that actually means is we're doing a projection onto the +1 eigenspace of this P Pauli string. And the reason we can do that is because we know some anti-commuting stabilizer Q that existed before doing P. And if we apply Q when we get a -1 result, we actually flip the sign back to plus. So in that sense, it's very easy to derive the Pauli corrections necessary to push your circuit into the +1 eigenspace. So out of the two, let's look first at the more interesting case, which are these Pauli-generated rotations, e to the I phi p. Such a rotation we can decompose using an ancilla qubit. We can put the rotation angle onto the ancilla and control on the ancilla and apply this P unitary. Now, if we have a control P gate and we assume P decomposes, say, on 3 registers, then we can actually write this circuit here as a circuit that acts on 3 different code modules. So let's say P1 was on 11 qubits and P2 and P3 as well. Then this first part of the circuit we could write as a circuit that prepares a state in X, and those are control P1, a control P2, and a control P3 on 33 additional qubits. And we have some ancilla hanging around here for a good reason, because we can rewrite this circuit and use the ancilla to apply our control P gates locally within a code module. So now each of our control P gates are only within the 12 qubits that are given by, say, a gross code or a 2 gross code. And these ancilla here act as intermediaries. And of course, we can measure out ancillas in a basis of our choosing because we don't care about the information. So if we measure out these ancillas in the X basis, we can actually forget about the C naughts that happen at the end of this circuit. So the resulting circuit is what we have here on the right with control P gates on each of the individual modules and then some entangling operation at the beginning, here in red. But if you squint your eyes, this entangling operation is actually just preparing a GHZ state. And there are various ways to prepare GHZ state, but one circuit to do so is the following. I hope I'm not going too fast, but I will zoom out in a few slides if you lost track. If we are doing a rotation, then the first code module, it contains the following circuit where we only depict one end of the ZZ measurement to prepare the GHZ state. And our other code modules, they have some other simpler circuit which which has maybe 1 or 2 ZZ measurements here in front, and we only depict one. So now we use further identities to decompose these gates. These are, in the literature somewhere. So for example, a control P gate we can decompose into Clifford rotations, which commute with the Z measurement. We can move them to the front. And then we use the fact that if you have anti-commuting polys, then we can turn rotations back into measurements. So if we have a Clifford rotation like Z tensor P1, preceded by an X measurement, which anti-commutes with the Z here, we can turn that back into a measurement. So you can turn rotations into measurements and vice versa. And this P1 Clifford rotation we can compile away using those standard techniques I mentioned very briefly, because you can push these Cliffords to the end of your circuit. So to kind of recap, what we did is we took our poly-generated rotations and poly measurements, which I didn't go into detail yet, but we decomposed them to act on each of the code modules using some simple inter-module measurements that are bicycle instructions. And what remains are these Y tensor P1, Y tensor P2 gates. Those we need to decompose further, but maybe in the interest of time, I will skip those slides. I don't know if there's any questions, but and the small angle rotation here, the Y minus phi, also has a fairly standard way of decomposing. Maybe Ross and Selinger, if you're familiar with it, have an algorithm from a few years ago that allow you to implement a small angle rotation to some arbitrary accuracy epsilon in a circuit depth that is logarithmic in your intended accuracy. Okay, so I will skip this, but this might be interesting in that if we want to implement a measurement Y tensor P1, then these instructions are not native to the architecture, so we need to decompose them into a long sequence of Clifford rotations followed by measurements, etc. And the overhead that is incurred when you do this, we characterized for all possible poly strings of length 12. So in fact, you can see that in this log scale plot in the y-axis that most poly strings, if you want to measure them on a gross code, require more than one measurement. In fact, the mean is about 18.55 for the gross code, and the 2 gross code is very similar. But in practice, actually, we can optimize the first register, so the means are 18.48 and 18.58, so we get this right plot as our distribution. And this is actually one of the things that gives us a larger time overhead when we compile our circuits, because you could imagine this being of roughly an order of magnitude slower than the surface code architecture when measuring an arbitrary polystring, because you have this factor 20-ish overhead in measuring a polystring. Okay, so now that we know how to compile, I can explain how we got this plot here. So we consider simple circuits of the following form, where we have Qj poly-generated rotations of some small angle phi j, and after compiling using the techniques I really briefly showed you just now, we can compute a simple additive failure probability where we take the failure probabilities from that table that we use the extrapolations for, and we also include any required idling. So some modules might be idling when you perform your circuit because you're, say, injecting T states, and injecting T states takes a long time. So if we consider random circuits, which give us our capability estimates of that large plot that I showed you, We fix the angle to be pi over 8, so each of these are equivalent to, say, a T-gate up to Clifford conjugation. Then we see, and then we set the failure probability to be at most 1/3. Then we see that, then we get that plot that I showed you earlier. And maybe, one thing you should hopefully roughly get out of this is that for a comparable number of T-gates, so, say 10 to the 15, we have roughly an order of magnitude more logical qubits than the comparable surface code. However, the number of time steps that are needed to implement one rotation is maybe roughly an order of magnitude worse. So that's definitely something we still want to work on. Yes, question?
So would you say that for the foreseeable future, what really matters is number of logical qubits, that somehow the number of steps is relatively irrelevant?
Yeah, so that also depends on what a time step, what time scale a time step is in your architecture. For us, the time scale for a time step is I think it's like, yeah, it's maybe relatively quick, but you could imagine that if you have if each time step was very slow, then yeah, you might run out of patience for running your application.
At least for those setting up, once you're high enough distance, you can drive the down and thereby have a deep circuit. So is that the thinking that as long as you increase the number of logical qubits, you keep push the depth out, that would be the case?
Yeah, so in these kind of estimates, it's actually, because we have a fixed number of physical qubits, you can't just arbitrarily increase the code distance to reach your target. Because if you increase the code distance, you require many more physical qubits.
So what would the effective error rate be at the largest qubit?
So the effective error rate, it was listed in this table that I showed you a while ago. Is if I'm interpreting you correctly. So if you have 10 to the minus 4 physical error rate, then say an architecture with 2 gross might have 10 to the minus 20-ish in module measurement error rates. But since the gross and 2 gross code are fixed in their code distance, we cannot just up the code distance to suppress the error even further. We would have to find a different code. If it,
that seems like multiple operations.
yeah. So as I showed you in the I'm getting back to the slide. In this plot, if you have 10 to the minus 4 physical error rate, you are already quite capable at executing many applications. If you are given enough physical qubits to work with. Like you could do chemistry or crypto. Yeah. Any other questions? Okay. So another thing we looked at was this transverse field Ising model. So we choose the same parameters for a 10 by 10 2D transverse field Ising model as in an earlier paper. And let's say we require that the accuracy is 10 to the minus 3. Then the resulting circuit has about 10 to the 5 Pauli-generated rotations with some small angle. And if we use the gross code architecture, the bicycle architecture with the gross code, then given a certain physical error rate, this architecture gets the following circuit failure probability. So you can see that we require less than 10 to the minus physical error rate for the bicycle architecture with the gross code to be able to do transverse field Ising model simulation at an accuracy of 10 to the minus 3. 2.1 times 10 to the minus 5 is where this intersect is. So if we compare that to a surface code architecture, the surface code architecture of distance 7 requires about 10,000 physical qubits, whereas the bicycle architecture requires 5,000 physical qubits. If you increase the distance, you require 17,000 physical qubits, but then, obviously you have suppressed the physical error rate. So, depending on how good of a qubit you can fabricate, you might, choose one of these architectures. For the 2-gross code, the numbers are much better. The 2-gross code has a larger distance of 18. I'll click 2 more times and then I'll get to you. And this 2-gross code architecture requires 8,000 physical qubits, and the physical error rate required to do to this transverse field Ising model is 7.3 times 10 to the minus 4. So that's this intersect here. A comparable surface code architecture has about 60,000 qubits for a distance 17 surface code and 72,000 or 73,000 qubits for a distance 19 surface code. So, question?
About your first 2 lines, I think earlier you had like a factor of 10 or so between the number of qubits. Where did that get lost?
Yeah.
Operations? Or?
Yeah, so if you looked at the, actually it's not that far away, so I can just click this one. You see that for gross code, so small systems, the difference is actually only about a factor 2. Oh, you mean in
like in the
physical qubits?
Slide you had, you said the bicycle code coding for maybe 12 qubits at the same number of qubits as the surface code 1.
Oh, okay. So there are some additive overheads, like for example, we need a magic state factory for each of these architectures.
These are just more complicated for these codes, right?
We use the same factory between the two. I mean, it's sort of plug and play which factory you use. So to make it more comparable, this additive factor is the same between all these 3 lines. Yeah, I can't think of right now why this factor is this, but you can see that the factor 10 is roughly returning when we look at 2 gross. Yeah. So I would have to kind of check my calculation to see what happened there. Any other questions? Okay, so to conclude, we think that the bicycle architecture satisfies, our 6 criteria for a scalable fault-tolerant architecture, going back to the previous slide. So, first off, it is fault-tolerant, so the logical errors are suppressed enough for meaningful algorithms to succeed. We think this architecture is addressable in that we can prepare individual logical qubits and measure them, arbitrarily. This architecture is universal in that we can do arbitrary quantum instructions to some, obviously to some accuracy. But moreover, we think that our architecture can be adaptive in that our measurements can be decoded in real time using this relay BP decoder or some improvement of it, and these results can then be used to alter future instructions. And this is very important when you do a magic state injection. Moreover, this architecture is modular in the sense that it can be distributed over many modules that are replaceable. So if you fabricate some faulty chip, with some probability, you can many of these chips you will succeed, eventually in fabricating an architecture. And this all comes down to that the architecture is sufficient in that, we can execute meaningful algorithms with reasonable physical resources. So some opportunities, for improvement. First off, the synthesis of the Pauli measurements I showed you has about a factor 20 time overhead, which would love to push down to be more comparable to the surface code, which needs only about a factor 1 to measure arbitrary Paulis. the poly-based compilation scheme we used, it leads to sequential T-gate execution. So it's very sequential, and we would like to inject many rotations simultaneously. All right. Yeah, so globally, actually, because the circuit if you are given a Clifford plus T circuit and you perform this poly-based compilation scheme, generally your result will be a rotation that acts on the entire system globally, and then another rotation that acts on the entire system globally, etc. Right? So each of these require all the qubits to cooperate, global entanglement to implement, and that's what I mean by sequential.
So it requires global entanglement to implement a single T.
So to inject a T-gate, that happens locally, but to do that rotation, it's e to the I pi over 8p for some poly that's supported on the entire system. That would be a global operation. So it's like a T-gate conjugated with an arbitrary Clifford circuit. That operation we can do in sort of constant depth. But this Clifford circuit can have arbitrary support, so it generally requires serializing all these operations. Yeah, question?
In the same vein, for the surface code comparisons, were you also doing quantity?
Yes. Yeah. Okay. So one thing that we would like to improve is the speed and accuracy that the decoder works. And as we saw, it's still quite slow to simulate it in software for the larger systems that we're interested in, say the inter-module measurements or the in-module measurements for a 2 gross code. And furthermore, we are interested in, say, increasing the code distance further, like finding other codes that suppress the physical error rates, and using the long-range coupling hardware that we've developed. We can consider a wide variety of QLDPC codes. We could further simplify the circuits that we have for bicycle instructions, especially those operations we think are high in error rate, and perhaps we can improve the T factories further in a way that uses this higher connectivity. So, and that's the end. So thank you all for your attention.
Thanks very much, Eddie. Other questions? So quite a few.
So can we go back to your scalability criteria?
Yeah.
So the you mentioned addressable.
Yeah.
Is it entirely clear that for algorithms of interest that's required?
That it is required. I mean, I guess you could always come up with an algorithm that requires to measure only a single qubit, let's say, if it's a decision problem. But in general, if you're given an arbitrary algorithm, without knowing ahead of time what it's going to be, you need to be able to address and prepare states in any of your qubits. If you allow them, if you allow sort of arbitrary state preparation. I'm not sure if that entirely addresses your question, but I gave it a shot. Maybe, are you satisfied with that answer, or
I think
a follow-up
it just
question?
seems like an interesting question, because how do you know? Like, so if I give you an algorithm, then you say, oh, I have to make it, and I give you an algorithm, I say this is what I want.
Yeah.
Why don't you tell me, oh, you actually gave me a bad algorithm? You should give me a slightly different one, and actually you can still do roughly the right thing, but we'll have to play these tricks.
Yeah,
I feel like it's not. Maybe it's clear. I personally find it unclear. but maybe it's already there.
Yeah, yeah. I mean, if you have some kind of co-design process, you can modify the algorithm to fit the architecture better. And you know, I think that's likely to happen for the foreseeable future for the largest experiments that we're going to see. But eventually, we want to scale this device so large that it might not be possible to, you know, go in and modify everything so it fits.
Any more questions? Okay, we already had quite a few during the talk, so yeah, let's thank Eddie again. We have a lunch break now, and we will reconvene here at 2 p.m. for a talk by Dripto, and then